This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome everybody. I'm Barry Sanders, one of the two co-chairs for the conference. In our infinite wisdom with the conference, we scheduled the conference during American Thanksgiving, which is like Christmas here, so it's the big holiday, which meant that a lot of Americans weren't able to attend the conference. But the four you see on the screen, who are going to introduce themselves, have kindly agreed to speak remotely. So whereas the conference is fully in person, this is the one remote session, or meant to be the one remote session for the conference. It's 1 hour long. We'll start off. Each of the four will introduce themselves and a brief thought on the topic of this session, which is the future of quantum computing. So they'll each talk for 5 minutes. Then I'll run a back and forth where those four and I will have a discussion about points, and then I'll turn it over to the audience for questions. People have microphones, and so as long as the people on the screen can hear you when the microphones are on, that'll be good. Okay, so we'll have our hour. We'll start off with 5 minutes by each of them. Okay, so Scott, can you speak for 5 minutes?
Sure. So it's great to be here virtually with three colleagues with whom I go back almost a quarter of a century. As scared and depressed as I feel right now about the future of the world, I'm feeling kind of good about the future of quantum computing. My situation is, I just took 2 years off from quantum computing to work at OpenAI. In an AI safety and alignment team that no longer exists. But I'm now sort of getting back into quantum computing this year. I'm sort of looking around saying, what have I missed? It's true that right now AI is sort of a lumbering giant that just sort of towers over everything else. But if you sort of took that away from the picture, you would have to say that quantum computing is in a really exciting time right now. I mean, it's only within the last year that we have started to see, I would say, genuine logical qubits that can sort of, outperform the underlying physical qubits, and that, look like, that they sort of could be a building block of a future a scalable system. We now have 2 qubit gates, physical gates with about 99.9% fidelity in trapped ions and other systems. Depending on how you look at it, that's either very close to or already at, the threshold for fault tolerance. So, that was not true for, the vast majority of the time that I've been in this field. Like, people talked about that, dreamed about that. But, the numbers, if you just look at the error rate as a function of year, it's gone down and down. And now we've reached the point where I think within the next decade, it is entirely realistic to be talking about, doing quantum simulations that would be hard to reproduce with a classical computer, and that at the very least would be scientifically interesting. Okay, to people in material science, in chemistry, in high energy physics, in other fields that care about quantum simulations. And then, once that bar is cleared of scientifically interesting, then one can work on the higher bar of commercially useful to the battery industry or the photovoltaics industry or whatever. Amazingly, despite all the progress there's been, I would say we still don't have a clear winner among the various architectures, as in, there is still a live race among trapped ions, neutral atoms, superconducting qubits, photonic qubits, which is not to say that some haven't made more progress than others, but I think there is very much still a live race. Now, in terms of algorithms, I guess the recent progress is a little less dramatic, but still very nice. I mean, after 30 years, I would say we still have not seen any breakthrough in quantum algorithms that is at the same level as Shor's and Grover's algorithms in the 90s. But maybe that's an unfair standard. They were just some very low-hanging fruits that were picked. And I would say the closest that we've come, actually, to meeting that standard has been achieved by actually all three of my fellow panelists. So, kudos to them for that. There have been some exciting developments in quantum algorithms. I was excited by what Stephen Jordan and others did in the past year on adapting the Yamakawa-Jandry breakthrough from a couple years ago to get a new quantum algorithm that can get a better approximation ratio for some NP-hard optimization problem. Some problem with some algebraic structure in it. But there surely is more to be discovered in quantum algorithms. But what I tell people is the biggest applications that we know about remain quantum simulation plus breaking the public key encryption that currently protects the internet. And the latter is not necessarily a positive for the world. And so, the onus is very much on us to expand the list of applications. Of course, we know many Grover-type speedups, which are, it'll take a very long time until those become a win in practice. We know other algorithms, quantum walk algorithms, QAOA, and so forth, that might sometimes give us speedups, but they remain very much subjects of active investigation. So anyway, I look forward to trading views about it with the other panelists.
Okay, thanks very much, Scott. So Aram, please introduce yourself and then speak about...
Great, yeah. Thanks, Barry, for inviting me, and thanks, everyone, for showing up. My name's Aram Harrow. I'm a physics professor at MIT, but I do quantum algorithms, quantum information theory, connections to many-body physics, all the theoretical side of things. And I was trying to think about what I wanted to say at an AI-oriented quantum conference. Yeah, I don't want to take too long because I do want to get to questions and discussion, but I'll share a few thoughts. So one of them is AI has been very hot these days. It's it's really, I think, been very exciting to watch it, its trajectory, to see its impact on things, as well as like the promise of it. But it's also something where when you think about the future of AI, like where will large language models be in 5 years, there's a lot of uncertainty because you can't prove anything about them. And there's when you think about the advantages of quantum computing, it's worth keeping in mind that part of why we are confident in them, even though we only have 100 qubits that can do 1,000 operations or so at the moment, is this provable guarantee that they come with. And so it's been a thing that the field has relied on. It's sort of through this long winter of whatever you want to call it, of not big enough quantum computers, we have faith in the theoretical exponential speedups. And those have been really a guiding principle throughout, and they seem to be getting close. And it puts it in an uncomfortable situation with AI, because when you think about quantum machine learning or AI generally you would expect it to work in regimes outside of the provable regime. The data is usually too messy to characterize. The models have, they're Turing complete, and so you would not expect to be able to, in general, expect that the optimization over them to be NP hard or worse. It's just sort of a feature of them that they're too complex to be able to pull things out. Like maybe have a theorem or two to go along with our intuition, but sort of broadly speaking, they're beyond, they're running beyond the range of theorems. Like maybe gradient descent works near a local minimum, but we're running it well outside of that regime. And so it's going to be an uncomfortable fit to match this sort of necessarily empirical field with a very theoretically oriented field of quantum computing. So I think, I don't have an answer to that, but I think it's an interesting challenge for the whole field. The other one, which a few of us have written about, sort of talked about it on and off, is if you had a QRAM, everything would be great, but we don't, and so we need to think about how are these algorithms going to work in an end-to-end manner. And there are a number of related things that go along with it, like how excited should we be about polynomial speed. And I think there's a lot of room for more thought about these types of questions. For example, so to be more concrete, quantum simulation has some exponential win, but a lot of the questions you want to answer are more than just simulation. Like you might want to say, what is the configuration of this molecule that has the lowest energy? Or what is the free energy of binding of this thing? And that's going to involve some tasks where you get an exponential win, and some things where maybe you get the square root advantage of Grover, or maybe you get a heuristic advantage of some machine learning technique. And so I think it would be one thing I would like to, I hope to see more in the quantum learning research of the future is how does a heuristic and possibly polynomial advantage combine with some of the known exponential wins in order to get an overall effective algorithm. Because if you exponentially speed up part of quantum simulation, but then other parts still bog you down, then you've lost advantage. I think that's all I want to say for now. I'll pass on to the other panelists and look forward to the discussion.
Thanks very much, Aram. So Andrew, please introduce yourself and then speak to the topic.
Yeah, thanks, Barry. Thanks for the opportunity to speak as part of this panel. It's great to be here with my fellow panelists. So I'm Andrew Childs. I'm a computer science professor at the University of Maryland. My research is mainly on quantum algorithms. Yeah, I mean, I think a lot of great points have already been made about the future of quantum computing. I guess maybe the thing that I would like to emphasize, which I think has already come out in the discussion so far, it's just that there's a lot of uncertainty about what quantum computers will be good at. So, as Scott mentioned, we have a couple of applications where we have, pretty good reason to think quantum computers offer a lot of advantage, for cryptanalysis, for simulating quantum mechanics. And beyond that, there's, hints and ideas and a lot of interesting things to explore. But, because we're in this kind of world right now where we don't have large-scale quantum computers to try things out on, we have to rely on, as Aram was talking about, proofs about the performance of quantum algorithms for the most part. So, I think because we know that for quantum computers to get significant speed up, they need to have some kind of special structure that they can take advantage of. They don't offer really significant speed ups for unstructured problems. We don't expect to be able to just throw them at anything. There has to be something about the problem that we try to approach with quantum computers that provides some reason for them to have some structure that they can latch onto that allows them to have a significant advantage. I think we don't have a great understanding of what exactly those structures look like. We have some examples, but and some things that we would like to explore. But it's definitely incomplete. Sort of our understanding of where we expect to see quantum speedups. So, I mean, I think that's both, it's exciting because there are many things to explore. There's a lot of possibilities. We may find that there are significant quantum speedups for problems that we, haven't even yet envisioned that, they might be good targets for quantum computers, and maybe we'll, hopefully we'll learn those things more and more as, we get larger scale devices that we can try things out on. I think the experimental advances, as Scott was describing, have been really, very impressive in recent years. And it's really exciting to see, how things will change as we have larger devices to try things out on. But I think there's a lot of, it's unclear what are really good targets for quantum computers. I think even for, let's say, quantum simulation, which is, I think a lot of people argue it's maybe one of the most compelling applications of quantum computers. I've certainly argued this because it's something that they're naturally suited to do, and it's something that if we want to understand things that behave according to the rules of quantum mechanics, it seems like those are things that should be hard for classical devices and that quantum computers should be good at. But it's not always so straightforward because there are often methods that have been developed just using classical computers or using, theoretical ideas that allow us to get an understanding of, some kinds of chemical systems or materials. I mean, people do a lot, computational chemists do a lot, let's say, with the, tools that they have at hand. So, when we're trying to do something useful with a quantum computer, we're up against, the difficulty of building a coherent quantum device that can do complicated calculations, and also the fact that, even classical algorithms can do very, very clever things. So it's, that makes it a complicated picture about where we could hope to see advantages from quantum computers. I think it's something that needs, a lot more exploration. But I think, we need to be sort of cautious about sort of our hopes for what we might expect to be able to do with quantum computers, and I guess only time will tell. So maybe I'll just stop there, and happy to pass things on to Eddie.
Okay, thanks, Andrew. And Eddie, again, introduce and speak to the topic. Thanks.
Hi, my name is Eddie Farhi. I was trained as a particle physicist. And in the late 90s, I got turned on by the idea of quantum computing, and I switched my interest. And I stayed working on quantum computing since then. My main interest has been the development of quantum algorithms. I'm sort of eternally optimistic that a quantum computer might be good for optimization. And let me see, about 7 years ago, I actually started working for Google. So I'm a principal scientist at Google. That's my employer. I'm not a mouthpiece for Google. I say what I want, but I am a Google employee. But I still hang out at MIT. In fact, I saw Aram today at MIT. Now, the development of quantum algorithms is a tricky business because, the usual standard is that people want us to prove that things are capable of doing things. And proving things in a computer science language often means showing things in worst case. But when I first went into quantum computing, I started talking to Michael Sipser. He said, there's no such thing as the set of worst case instances of anything. And I didn't really know what that meant, but it took me a while and I kind of understood it, which is if you say what you think is a worst case set, if you ever look at one instance in it, you might be able to solve it. So there's no such thing as the set of worst case instances, and yet that is the standard that is used by computer scientists in asserting that things are difficult. You want to show that something solves everything, including the worst case. And I am intrigued by the possibility that quantum computers can solve problems in practice. Peter Shor gives a talk where he talks about the development of classical algorithms, and he talks about simulated annealing as one of 4 examples of classical algorithms without provable guarantees that work extremely well. And I run simulated annealing on optimization problems. I'm shocked by how well it works. And yet it's very hard to prove that it works well, because to prove it, you have to show that there's some Markov chain whose gap is not exponentially small, but it works. And so, I think that we should be open to the possibility that we can explore quantum algorithms without proof necessarily, but we can still learn things by trying. We can learn things by simulation. Now, the ultimate way we would learn things is if we could run these things on a big quantum computer. Unfortunately, that's not going to happen very soon, because even if you try to run things on an existing quantum computer, the limited size and the noise means that the performance, even of a perfect algorithm, will be degraded, so that it's hard to judge its performance. But ideally, if we had an error-corrected device of a sufficient size, we could do experiments on it that go beyond what we might be able to achieve by classical simulation or by classical analysis of a certain size, because you can use like tensor methods and all kinds of things to analyze the performance. So I'm open to the possibility of learning things about quantum algorithms without necessarily proving that they work in worst case. And I think we've learned a lot of really interesting things about quantum algorithms that are not simply associated with that one particular line. Now, and so I remain a practitioner. I don't I don't really like to talk about whether I'm optimistic or not. I just decide what I'm going to do. And what I do is I work on things, and that speaks to the fact that I think they're not crazy. And that's good enough to keep me going. I would like to say, so, it's very hard to make predictions, especially about the future. So instead, I would like to, talk about I think I can only talk about what I do. And what I do is attempt certain mathematical approaches to quantum algorithms, which are either successful or not. I want to say one other thing about simulation, which people were talking about regular fault-tolerant quantum computers. But there are other platforms. For example, there are people, for example, today Aram was talking about the Fermi-Hubbard model at MIT. But people have optical lattices with 600 wells in which they put fermions, and they can't put two at the same spin in the same site. And they measure properties of the Fermi-Hubbard model. Now, there are questions whether the things they're measured are still simulable or not. But there are things, if you're interested in physical simulation, there are things which are not just gate model computers, but beautiful atom arrays, which are, they're way colder than superconducting devices. They're technical marvels. And they have 600 fermions. And there's no sign issue problem because they've got 600 fermions inside of the wells. And you can't put two in the same spot. So what I'm saying is the sign problem is solved. And so I think that there are ways we can look, there are physical systems which are interesting beyond gate model quantum computers. That's all I wanted to say.
Okay.
Thank you.
Thanks a lot, Eddie. Thanks all of you for the comments. I'm just thinking about things to discuss as you're speaking. One, so Aram mentioned explicitly the algorithm versus heuristic comparison, and then that's come up in all the discussions in various ways. But, like when we go to, Scott, you used the terms from, the polynomial hierarchy for decision problems. So, like we have the sense of, the algorithms, the rigorous proofs of the complexity, the worst case scenario. But a lot of people at this conference in working on the intersection between AI and quantum computing are doing the messy heuristic tests. And it's come up in the discussion, so there's I did some stuff a number of years ago where I bought time on D-Wave and I bankrupted myself before I was convinced that I saw anything meaningful. So the point I'm trying to get at is, in this messy world of heuristics and empirical studies, at what point is a result convincing in showing a quantum advantage? And then whoever wants to speak, go ahead.
Yeah, so we now have almost 20 years of people trying out heuristic algorithms, originally on D-Wave devices and now on a wide variety of devices. Of course, for even longer than that, people have been running classical simulations to try to understand empirically the behavior of quantum algorithms beyond what we can prove. And I should say that is absolutely an essential thing to do, and we should do it. I think the fundamental difficulty is that it's not enough for your quantum heuristic to do well. It's not enough for a quantum heuristic to beat the classical brute force or classical exact algorithm. Rather, the quantum heuristic has to beat the best classical heuristic that is out there. Right, so we have to do a head-to-head comparison. We have to make it as fair as possible, and then what we want to see is not just that like for example a quantum device is winning by some constant factor, where that might be for problems of finding the ground state of this particular quantum system. Right, so then you would say, well, it's no surprise like that, this system is very good at finding its own ground state, and even if I removed quantum behavior from it, it still may have been good at that, right? What we want to see is sort of better scale it, right? We want to see, and in particular, we want to see sort of better performance that is because of quantum interference in, among entangled states in an exponentially large Hilbert space, and that is not because of any other reason. Right. And so I think, it is hard to do science about this, if you want to, our, experience of the last decade or two has underscored what a lot of the difficulties are. But I mean, basically, what I want to see is, first of all, like every day or week, I'm seeing papers on the archive about, quantum approach to such and such, either quantum neural nets, quantum finance, and often it doesn't even reach the point of doing the comparison against the best classical algorithm that we know. Okay, so then that can just be discounted right away, right? If you're just not doing the comparison, then, we're not asking the central question, right? But then, once the key question is asked, then what we want to see is sort of better scaling behavior, and ideally to to have some sort of story about what is going on. Like this is a tunneling effect, like we saw in the quantum walk on the glued trees, right? Or this is a Grover type speed up, right? Something that helps us understand, why should we expect that as we scale up to larger and larger systems, this speed up will not go away, but will rather get better and better.
Okay, I'm going to object to that. I mean, I think it's just so narrow to have one criterion for deciding whether a paper is interesting, which is whether there's evidence that it beats the best classical. Like, I work on the QAOA, and there are really interesting phenomena on the QAOA where it seems like if you look at the parameters of which you use to optimize the QAOA, they fall on universal curves. Now, understanding why the parameters fall on universal curves, we see this in different settings, is itself interesting, but it doesn't address the issue of whether the algorithm is better than classical. So there are tons of questions you can ask about algorithms, which are not simply the only question which I hear about, which is, does it or does it not beat the best classical algorithm? There are other things of interest to people who pay attention to the field.
Without doubt, there are thousands of interesting questions that you could ask, and people are free to write papers about any of them. Now, when I'm out there talking to people in the investment world or the funding world or journalists, every week, I am dealing with people who see all these papers and have taken from them the impression that, well, there must be a quantum advantage for all these tasks that is known,
Okay.
or else why are people writing all these things about it?
Okay, well, that's your burden, that you feel like you have to defend.
That is indeed my burden, and
that's your burden that you have to.
That is what I deal with. That I think we have to look at what is the sort of perception in the external world, and it's that quantum is a synonym for awesome. Quantum speeds up everything, right? And in particular that we have quantum image recognition, quantum handwriting recognition, quantum neural nets. I mean, we've seen companies go public on claims about these kinds of applications, or pitch to investors on these claims, and they say, well, look, there's papers about it. And so I think sometimes it's not enough when writing a paper to not say anything false. Rather, in an environment like this, one has to anticipate and head off the ways that people are going to misinterpret things.
Well, I don't understand this. I don't feel this burden whatsoever. I don't care.
All right.
I just don't care. I find it odd that you feel like this is, something you have to fight for. I mean, I don't care what people say. I don't care what people say after they read my papers. I just care that my papers are correct. That's it. My papers are correct, period.
Oh, okay. I mean, I would say if some people don't feel the burden, then that doubles the burden that other people have.
Oh, well, gee, that's a very transactional way to put it. Okay, fine.
I want to come back a little to Barry's question. I mean, it's a good question of like, how will this be received and what should the impression should you give? But just like, if you're playing around with the D-Wave machine, how should you feel about what you're seeing? And I think you need a mix of some empirical and also some like rigorous example of toy problems, which, along with what Scott was saying, like fortifies your idea of a story. Like, you could have a story like tunneling or symmetry or periodicity, and then your thing doesn't exactly obey that, but you, like, maybe you've seen it work, toy problem, and you have some argument about why the instances you're looking at resemble that. And I think it's true that ultimately, if you want to know if there's going to be a speed up, you want to compare against the best classical heuristics. But it's tough because those are also much more mature algorithms. So one analogy I think is good is like in cryptography, like you're trying to ask a question of like, will we ever find an algorithm that performs the algorithms we already know? And that's kind of like people study in cryptography. Like, it's a lattice cryptosystem. The standards do this well, but if you thought about it for 20 minutes, you do better. And you have to ask those kind of questions a lot. And one thing that people do when they're looking at random number generators is they say, well, before we can solve the attacks, let's just look at some of the summary statistics, and do those look plausibly random enough? So, yeah, I mean, I guess I don't have a clear answer to it, but some comparing with the obvious algorithms and having a toy, trying on some toy examples, I don't think you always have to compare it against super optimized thing. If there's some structure the quantum algorithm can't see, but manages to have a step for without being explicitly told about that structure, and then there's a classical algorithm where if you explicitly told it about the structure, it can find the speed up. I wouldn't discount the quantum algorithm in that case. Like we're having this discussion about recent QAOA speed up by Ashley Montanaro and Leo Zhu, which looks really awesome, but is on a structured instance where very possibly there's a classical algorithm that could also recover that advantage. And I don't know, I think you have to keep investigating the classical algorithm, but it's hard to say that there's nothing. When you see a quantum thing running quickly, it's hard to totally discount it and say that there's nothing there. Like there's a lot of room for creativity in the classical algorithms that beat the quantum one, but also if there is some quantum phenomenon there, then there are a lot of twists that you might do to improve the quantum algorithm. And it's hard to write something off even if it doesn't outperform classical.
Yeah, I mean, I think from a pragmatic standpoint, like, if you sort of are able to solve a problem with a quantum computer that you wanted to solve and you hadn't previously solved it, and you've been able to solve it with a classical computer, then you will have done something interesting. And so, I think if we're able to, let's say, use a quantum computer to design some material that's useful, we build the superconducting device with some material that we designed using a quantum computer. It sort of doesn't matter if maybe we could have come up with an algorithm to understand that material with a classical computer. It will have been a useful thing to do. I think perhaps from this perspective. We want to understand what quantum computers are good at, and we're going to do that by sort of, looking at toy examples and trying to come up with explanations of why our quantum algorithms are behaving. And we should absolutely have those kinds of things. We should do that. But ultimately, hopefully we will actually use them for something that somehow, people are really interested in doing. And I think maybe that's at some point, the gold standard, that we were able to break some code that people tried really hard to break with classical devices, and they weren't able to break it, or solve some optimization problem, that we weren't able to, get the answer to classically, and we were able to get it with a quantum computer. I think it's unlikely that we will be able to do those things by sort of like fumbling around in the dark. Like there needs to be some guiding principle. We need to have some understanding of what are the structures that we can really take advantage of. But I think, sort of how we'll really know that we've done something that somehow, quantum computers were really useful for is when, we get the answer. We wanted to have that answer, and we weren't able to get that answer another way.
I mean, hopefully all of us can agree that the ideal here is open exploration, where, everyone is thinking as hard as they can about quantum algorithms, both theoretically and empirically where relevant. Everyone is also thinking as hard as they can about classical algorithms, and they're trying to do the comparison in as, scientific a way as possible. Now when there's, strong financial incentives, sometimes that tilts the scales in a particular direction, and you get people who, sometimes I think in science, it's never enough to only say things that are true, right? You want to, we sort of have a higher standard. You should tell the whole truth, right? And, sometimes when I'm reading, quantum papers that are boasting about how great something is, right? I want to, I'm asking not just are they telling me the truth, but are they telling me the whole truth, right? What are the caveats? Are they being, do I have to dig into the appendices to, see what the caveats are to this algorithm? I think that it's on us to be open about it, to sort of right there in the abstract or the introduction to say, well, okay, but of course, it only works on these structured instances, or of course, there's also a classical algorithm to do such and such. I think, what was I going to say? That it's true that sometimes you can find a quantum algorithm more easily than you can find a classical algorithm that does the same thing, even if they both exist, right? So you could say, okay, well, we have an additional resource, besides running time, we have, human brain time, right, to come up with the algorithm, right? But I think we have to guard against the what I've called the stone soup phenomenon, right, which is where everyone gets very excited about doing something with a quantum computer, and for that reason, they put massive effort into understanding some particular problem, and therefore they make progress on the problem. But if they had put equal effort into classical algorithms, they also would have made progress, right? So we have to try to separate out the component that is really coming from the thing that got us all excited about quantum computing in the first place, which is the ability to choreograph these patterns of interference to get a speed up over what you could have done with a classical computer. And I think the scientific challenge remains of sort of finding the set of problems where that really helps the most. So now Eddie said before, there's no such thing as a worst case set of instances, right? Well, I think you have to be careful there, because there is such a thing as a worst case distribution over instances, or like a distribution over instances.
That's going to get technical.
Yeah.
I'm not so sure about that either.
Well, no, you can have a district, like, for example, for computing the parity of n bits, right? We would say, if the bits are random, then the algorithm's performance, on that random ensemble is the same as what it is in the worst case. And, one can give an argument for that, a sort of worst case, average case.
Yeah, I guess I don't follow that. Maybe it doesn't matter, but I wrote the paper showing a quantum computer couldn't speed up the.
I know. That's why I mentioned it. I know.
Yeah. Okay.
Yeah, I know. But So I think figuring out for which ensembles of instances or which distributions of instances you get a speed up, and if so, by how much, and if so, what principles of quantum algorithms are being exploited there. I think that is we should see ourselves as working together on this scientific quest to try to understand all of those things.
Well, I guess my what I don't totally resonate with is this constant use of words like understanding, insights. I don't understand it. Like, for example, we have results on how the QAOA performs on the SK model. Mm-hmm. And we analyzed it at infinite size, And we prove theorems. We prove what the performance of the QAOA is at infinite size. We beat the best assumption-free classical algorithm at depth 11. Okay, we beat it. We beat the best assumption-free classical algorithm. I have no idea how it works. Zero. I don't know. I have no idea. Neither do any of my collaborators. I have no insight, nothing. And yet I know it works. And as you increase the depth, it seems to be going to Parisi. So, I just don't know why it works. I don't. But I did the calculation with my collaborators and we see results. I mean,
But wouldn't it be great to know?
No.
Wouldn't it be great to know how it works and somehow use that insight to do something else? I mean, wouldn't that be a good thing?
That'd be great.
Yeah, but I mean, I think understanding is overrated. I really do. I think understanding is an overrated concept. I'm not that interested in understanding. I'm interested in calculation.
I mean, I think that if we had a situation in quantum computing that is analogous to what now exists in generative AI, where we just have, these utterly civilization-changing, suite of algorithms, even though no one really understands how they work, and then we would have the luxury to say, well, just here it is, take it or leave it. But I would say that that's not the situation that we're in quantum algorithms. The situation in quantum algorithms is much more that we have speed ups mostly, for very specialized problems. And so we don't have the luxury of disdaining understanding.
Okay.
That being the case.
That's
I mean, I think, obviously we would like to have understanding, but it may never come.
Yeah.
And
I think understanding is a false idol. I really do.
Okay, so that was great. Fireworks, emotions. We love it. Okay, so we'll take a bit of time to go to the audience. And
Hello. Hi, everyone. Yeah, Maria. I think most of you know me up
they
there.
can't see you, though. So.
Yeah, exactly. Sorry. What you're saying is really, I think, absolutely crucial. Let me try to summarize it in my own words and try to then motivate for a third type of argument we should start to cultivate. So basically what you're all saying is that the computational complexity arguments that is the culture of quantum computing is not very useful in a field like machine learning, and I would almost argue in many quantum applications for real life. And I'm absolutely surprised that you all agree about that, more or less, and very happy to hear that. And now you're bickering around the idea of our second argument that we have, since we can simulate things or have toy problems.
Go to a question, though, if that's
Yeah. It's important, though. Oh, gosh, I feel like I'm in court. No. The second argument would be like, okay, can we, in heuristics, prove speed-ups or that one algorithm performs better than the other one, best known classical, and so on and so forth. But isn't there a third argument, and this goes to understanding, but I think a different way of understanding, not understanding why something is better, but a way of understanding why something works. And to give an example in machine learning, for example, if we can show that a reasonably unique quantum routine can reveal features that are just interesting for generalization, and we can show that this is interesting. That would be an absolutely powerful argument that I don't see in any papers at the moment, and that I think many more people should talk about and think about. And maybe, Aram, towards your little comment that machine learning is empirical, this is not true. This is true for deep learning.
Maria, it's not really a debate, so let's just go to a
okay,
question.
so last statement is, there's a lot of theory to machine learning that tells you what is interesting and it's not, but it doesn't live in deep learning, so it lives in statistics or other parts of machine learning. Sorry if I overstepped my time.
Okay, good. So we have some statements challenging the discussion. Do you guys want to make any responses?
When you said something about the culture of computational complexity, not being useful for what we're doing here. I mean, I think some parts are and some parts aren't, right? The part where you try to clearly define, what resources am I using? Am I getting a benefit, using quantum compared to not using it? Which were the questions that Bernstein, Vazirani, and Simon and Shor asked 30 years ago. Those remain very good questions to ask. I mean, of course, you can't answer everything that you want on the basis of theorems. And so, at some point you also do numerical simulations. You take any form of evidence that you can. But I think clearly defining, what you mean by an advantage, trying to quantify, is this just a constant factor? Is there better scaling behavior? I think those remain as relevant as they ever were.
Any other response?
Yeah, and I think, I think we're not that far apart. I think there's a role for theorems in machine learning, and we don't expect those theorems to fully explain what's going on in the algorithm. Even for something provable, like a kernel method or regression, you say, okay, well, the algorithm provably does solve this problem, but then how is it actually going to do on some out of prediction? That's going to depend on the details of my data. And I think I can submit that when you put the whole package together, you're going to be running it on something outside of the provable regime in the interesting cases. And I think that's even if it's not deep learning. We rarely are given a bunch of points that are a linear model plus Gaussian noise, and we know that that's actually the correct description of the model, for example. But for sure, it's still worth looking at the theorems. And maybe the question is then, what is the role of the theorems? And I view them as you get a really solid understanding of a toy model, which lets you guess about an extrapolation to the situation in front of you. So I think like the toy model has its use, even though it doesn't literally describe the thing in front of us, because hopefully it resonates some of the stylized features of it. So I think, I think we're describing different parts of the same elephant here. I don't think there's a dramatic difference.
Any more comments? Yeah, I don't hear anything. Is there another question?
Hello?
And then just introduce yourself and then short question.
Yeah, sure. So I'm Alex, and I want to connect to something that Andrew said in his introduction. Like there were two statements that I think are extremely important in the context of quantum computation in general, but that on a superficial level somehow seem sort of in contradiction with one another, and I'd like you to elaborate a bit on those. So the one thing is that quantum is good, not for generic things, but for structured things. So you need structure for quantum algorithms to be good, like let it be some Fourier type stuff. And on the other side, there's like the natural realm of quantum simulation, let's say, for example, quantum chemistry, where quantum is good because it's quantum. And this sort of is also somewhat a generic area, like some quantum problem, and it's sort of a generic statement that their quantum is good. So in a superficial way, these things seem somewhat contradictory. There's something generic, and on the other side, generic isn't really good for quantum. So is it that the notion of genericness is sort of wrong in a sense in this comparison, or is it rather that eventually, well, quantum simulation is maybe average case easy?
Okay, thanks. Anybody want to respond?
I guess I would say that probably the quantum dynamics that actually sort of are natural and that you can efficiently simulate, they actually are structured. They're special, right? So it's not like the dynamics of just any kind of arbitrarily connected quantum system can be simulated efficiently. But if you have a k-local Hamiltonian, or a system which is fermions interacting in a geometrically local way, or something which actually describes something that's kind of like a physically plausible system, those are the kinds of systems that you actually can simulate efficiently, and they do evolve in some structured way. So I think there is structure there. It's not the same as the structure that you have. It's not like there's only one kind of structure necessarily that quantum algorithms can take advantage of. There's the kind of algorithms that make use of Fourier transforms are perhaps doing something quite different than what happens in sort of the dynamics of k-local Hamiltonians, let's say. Although maybe you can have some mapping between them. But I think fundamentally I would say the answer is that there's structure in both of those cases.
I mean, I think maybe the deepest resolution of the tension that you identified is like we expect quantum computers to give big speedups for relatively generic quantum problems. right? For, problems of simulating, all sorts of k-local Hamiltonians, for example. But, to the very fact that we're talking about a quantum problem has imported all the whole structure of quantum mechanics, right? The much harder thing, the thing that requires, something a much more specialized problems is when you want quantum speedups for purely classical problems. When you want quantum speedups for things that have nothing to do with quantum mechanics, right? And then if you're happy with a Grover type speedup, then again, the problem can be pretty unstructured. But if you want an exponential speedup, then our experience so far has been, well, then you want something like periodicity, some sort of hidden abelian group structure, or, like a very special graph, like the glued trees graph, or something else of that kind that is just, specially designed to allow this destructive interference to happen on all the outcomes that you don't want, and constructive interference to happen only on the outcome that you do want. So I think that this need for huge structure is very closely correlated with trying to solve a classical problem.
Although that might also, what I'm not sure about is what extent that the need for structure, which for sure we've seen, might just reflect the need to be able to prove things. And like, we don't get to see all the
back to the research questions, right?
Yeah.
Okay, thank you. Oh, keep going.
Well, just for quantum simulation problems, there are many quantum simulation problems where chemistry and people don't know how to simulate them in a classical computer. They're a good deal less structured than the ones where we can prove exponential speedup, or to the extent that we can ever prove exponential speedup.
Yeah. I mean, within the black box model or the query complexity model, we can actually prove some of this stuff, right? Like we can look at unstructured problems, parity, or the OR function, or all sorts of total Boolean functions, and we can say the quantums, either there's no asymptotic quantum speedup at all, or the quantum speedup that you get is only polynomial. Whereas we can study problems involving structured oracles like Simon's problem, or Shor's period finding problem, or the glued trees problem, and we can say here the speedup is exponential. And there are very nice open questions. I mean, Andras Ambayanis and I, a decade ago or more, asked, can you ever get an exponential quantum speedup while querying a random oracle, right, for a decision problem? That question remains open. It might eventually get settled. But, the big breakthrough 2 years ago by Yamakawa and Jandry came when they, without answering our question, they changed the question. And they said, well, if we change our focus from a decision problem to a search problem, an NP search problem, then there is an exponential quantum speedup relative to a random oracle. And they showed exactly how. But it was precisely sort of probing this boundary of just how little structure can you have in a black box problem and still get an exponential quantum speedup.
I think that's right. But also I think another approach you can take is look at physics and see whether there are phenomenon which you can then translate perhaps into some algorithmic advantage. For example, quantum systems tunnel through wells, and you might ask yourself, can I set up a problem where the solution, it's some optimization problem where there's a barrier, and quantum mechanically I tunnel through it, but classically I can't overcome the barrier, and there are examples of that. So, or the things Andrew and I used to work on, which is how, propagating through all kinds of structures, you see that quantum things move faster than you might have imagined. Just like you just take the hypercube, and if you start in one corner of the hypercube and you quantum walk, you end up on the other side in time pi/2 or something, whereas classically you would just get lost in the middle. Then can you turn that into something, some kind of advantage algorithmically? And that's the kind of stuff Andrew and I worked on. So I think that's another approach to it, which is just look at the physics phenomenon and ask, is there something weird in physics that you can then take advantage of in an algorithmic fashion.
Yeah, and your group has had more success on that than anyone else has. So.
Okay, thank you.
Okay, thanks. So we have time for one last question. There's one at the back. Please introduce yourself and ask a short question. Oh, I don't. There. Oh, Abu Fazal? Okay, so go to him, I guess, and then over here. But short introduction, short question.
This is Abul. So my question is actually about the heuristic quantum AI. So what is a fair comparison in that domain between quantum algorithms and for example, classical algorithms? Because we have a small quantum computers and we have for example, if you think about the deep learning, we have classical algorithms with millions of neurons. So if you just look at the accuracy, I mean, what is a fair comparison? I mean, when can we say that our quantum algorithms are decent?
Okay. Yeah, question's clear. Any answer?
Well, I think part of the value proposition for quantum computer has to be beating an unfair comparison. Like the qubits are always going to be more expensive than classical bits. So, that's why we always need some kind of speed up. And so I think the quantum computer has to be able to, ideally a small number of qubits could beat a much larger number of classical bits. Failing that, maybe you're happy with a quadratic or, doesn't have to be quadratic, whatever, cubic, n to the 1.5, whatever, some lesser than exponential speed up. Because for various reasons, you might be happy with that. Intellectual curiosity, maybe this is going to be part of a larger pipeline and exponential speed ups elsewhere in the pipeline. For whatever reason, then maybe that becomes a valid part of the comparison. But yeah, I would push back on whether fairness is something that we should aim for in these sort of comparisons. I don't know what others want to add.
Yeah, I would say, we shouldn't think about this as if there's some rules laid down from on high about what counts or doesn't count as demonstrating a speed up for quantum machine learning. I mean, any type of evidence is fair game, but what I want to see is some process was followed that could have led to the conclusion that, there is actually no quantum speed up for this task or with this class of quantum machine learning models, right? I want to see that a sort of, it's not that someone just wrote at the bottom line, okay, we need to see that quantum is better or else we can't publish our paper. And so now let's go backwards from that to just sort of fill in the justification that is consistent with that, right? I want to see a process where we actually tried as hard as we could to to equalize what could be equalized, right? Study, for example, a small quantum neural net versus a small classical neural net, and say, is the quantum neural net getting an advantage that could not, as Aram said, that could not be easily replicated by just adding a few more neurons to the classical neural net, and then better yet, if we can sort of get some understanding of what is going on there. Why is that the case? So I think it's a very modest ask, and what's striking is sort of the a number of papers I've seen in this area that sort of don't even clear that, I think, very low bar of even just sort of noticing and asking these questions.
Okay, I think we're almost out of time, so we won't be able to take any more questions. I'm sorry. So we really appreciate you guys taking the time and sharing with us this direction and all the bumps along the way, and a very honest presentation, which is really important. And we'd like to wish all four of you a great Thanksgiving, and thank you very much.
Thank you.
Thanks for hosting, and thanks everyone for showing up.
Yeah, thanks a lot.
Yeah.
Good day.
I'd love to come to Australia next year.
Yeah, next. I've enjoyed all my trips there, and if I get family permission, I'll be back another time.
Yeah, well, next time we'll do it not during American Thanksgiving.
All right.
Yeah, thank you.
Yes.
Bye, everyone.
Bye. Thank you. Bye.
Okay,
Bye.
bye.
Everyone. Good. It was fun. It was a good time. Bye-bye.
Yeah. Okay, bye.